Now, hello everyone. Welcome to the final day of new content in ECE 2002. Riyadh had a question about homework 7, question number 4. Is there some sort of trick to it, or is it hard to get the right one? A series resonance circuit consists of a 0.4 ohm resistor in series with an inductor modeled by 20 millihenry in parallel with 2K. And a capacitor modeled by 50 microfarad in parallel of 10 kilo ohm. Assume omega naught is equal to 1 over square root LP CP. And then there's the actual instruction, which I had to go to Piazza to read because they get cut off from the original text. Homework 7, 3, and 4. Parts A and B cut off by formatting. And of course, I don't have it in my folder of secret, core staff things. So I actually have to look at the assignment. Can you just read me the question?
Oh, yeah, 1 second.
While I bring it up. Or I just found it.
Oh, okay.
Sorry. You get to see behind the curtain a little bit. It's not all very okay. I'm going to ask for a circuit diagram from Sophie to figure this one out. Because I'm having trouble just deciphering what the problem statement is.
Yeah, I had that problem too.
At omega naught, find QL of the inductor and QC of the capacitor. So for the part A, you just use the definition once you have your circuit drawn. The reactance at that part at that frequency divided by the resistance at that frequency. Same thing for the capacitor. And then at omega naught, find Q of the series circuit. Which I really need that circuit diagram. I'll send an email to Sophie and be like, for homework 7, question 4, please release a circuit diagram to accompany text description. I think that will help. Does that answer your question at all, Riyadh?
Kinda, because I draw the circuit diagram and I might be wrong, I don't know, but I just use the formulas that are on lecture set 3 for the quality factor of an inductor and capacitor. So QL equals W naught L over RS. Is that not what we're supposed to use?
Right, that's what you should use.
Oh, okay, then I might be just hit algebra error. Okay, thank you.
Right, yeah, you should be getting quality factors that are reasonably high, and by reasonably high I mean at least greater than 1.
Okay, that makes sense.
Yeah, I will. Boy, yeah, I just have a hard time deciphering it. It's a series resonance circuit. Yeah, it says inductors modeled by 20 millihenry in parallel with 2K. Like, it's definitely an interesting circuit model, to say the least. So definitely something that requires a circuit diagram to communicate. All right. Facts. Any other questions about homework 7? Which I should leave up because there's a chance I might have to unassign problems. And by unassign, I mean, just not grade them.
Not 7 and 8 though, please. Those are the easy problems.
You like 7 and 8?
Yeah, they were really straightforward. I mean, you just have to plug and chug.
Plug and chug. Okay. I will try my best to keep it in. Depends on how fast I get through material today. So I better not waste any time telling you about exam 2. So here are the statistics for exam 2. Grades are, your curve grades are out on Brightspace. We'll be releasing the raw scores over the weekend, but we got things done on time. Good for the teaching staff. Less than 168 hours to turn around this many exams is not bad. So the mean, the average, algebraic mean average, or excuse me, arithmetic mean average was 54.9. The median score was a 54.4. Okay, pretty good. I mean, it wasn't as high as 60 as I wanted, but it was still higher than the first exam by like 2 points. And then the mode is what tells you something's a little bit weird here. The mode was actually a 70. So the most commonly encountered score was actually a 70. And the standard deviation was 19.52, wider than the first exam. So that's also, not very good for those who are trying to blow this exam out of the park, and not good as an instructor because it means people could turn in relatively empty exams and still get a decent score. But after the curve, it was put at an 80 except for all the late scores, and the standard deviation was put at a 10. So if you look at the actual histogram of raw scores, you'll see that what's going on here is that we had a weekly bimodal distribution, by which I mean, instead of the normal bell curve, we got, the one hilltop a little early, a little valley, and then a hilltop, and then the rest of the bell. So it goes up, dips a little in the middle, goes up again, and then goes down. So that means, there's actually relatively few scores that were at the mean, compared to in the 40 to 50 range and the 60 to 70 range. So it seems like the class really split on whether this was, an exam where we should be scoring in the upper 40s and one where we should be scoring in the lower 60s. So you will see that when you get your grades back. Do we have any questions? Well, yeah, the mode of 70 is pretty high, but I think the next most common grade was like 50 something. Let me get it real fast. Yeah. Yeah, the next most common score was like a 54, and 47 wasn't very far beyond that. So like I said, bimodal, where there's not a lot of scores, exactly at the mean or median, but, there's higher concentrations of scores just outside of the mean. The mean after the curve should be an 80. It's actually like a 79.91 because some people turned in late and got a 10-point penalty. I was planning on keeping all the solutions for myself, but I guess because Mahir asked, I will release them to everyone. I think the zeros are included, or yeah, the zeros are what drag it down to. The raw scores are calculated without the zeros, so I don't let the zeros throw off the summary statistics of the raw scores. It's confusing. I have big Excel formulas taking care of all this. Let's see. Yeah. So yeah, actually, yeah, none of the scores include the zeros. So none of the statistics are affected by the zeros. How many zeros were there? A little bit private, but there were 3 people who didn't turn in an exam, and there's 2 we're still waiting on scores for because of submission difficulties. Any more questions about the exam? You should be able to see it on Brightspace. I hope everyone was, believe they got the score they earned. Oh yes, quiz 5. Thank you, AJ. So yeah, quiz 5 will start at noon, due by 11:59 p.m. tomorrow. Please do it. Let's see. As a hint, review Bode plots and review Miller theorem. And I think that's about all the hints I want to give you. So review Bode plots, review Miller theorem. You're welcome for grading those exams. I had to push a little bit harder, but it worked pretty well. Homework is going to be challenging to get done. I've graded some of homework 5 has been graded, but not all of it. And homework 6 hasn't been started yet. And then we'll have homework 7 due on Monday. Yikes. I just, knock on wood, we get all the homework graded before grades are due for this class. Other thing, thanks Aubrey for reminding me, but we need to, it really helps if you fill out the course survey for this class. Since I'm not faculty, I'm not tenured. So it really helps to have a good response rate on the course survey that gets released, every term. So if you could please take some time to fill that out, it helps me out and helps me keep my teaching positions. There's that. Let's see. Homework, quiz, survey, exam. Yeah, I'm not teaching this course anymore, but I'd like to be able to teach in the future. Oh, last thing. I'll put a post in Piazza. But if you are graduating this summer or in the fall, shoot me a message so that we can try to get your grades out ASAP so it doesn't affect any of your graduation things. So it would be helpful if you were planning on graduating this summer or in the fall, if you just let me know if you're graduating. With that being said, that's enough administrative things. Time to get into lecture proper for the last time. Lecture set 8. Here we go. Cool. So we're still talking about circuit elements at high frequency. And then we've been talking about transmission lines. So the TX line is a distributed circuit, not a lump circuit like we've been studying so far. The length of the TX line determines its stability of the model, and specifically the length compared to the wavelength for the specific, single frequency of radiation being considered. What if your signal has multiple frequencies involved? Well, you just usually compare it to the highest one present in your signal. So this is a very short length of the TX line we're looking at. So remember, TX line is just, a pair of wires where we have some sort of connection like this. So there's an incremental resistance and inductance, R sub L and L sub L, as well as an incremental capacitance and conductance, C sub L and G sub L, associated with this. We don't really have time to get into how you calculate these things for a given geometry. That belongs in electromagnetics. But we can just say we have these constants given to us, and we can calculate with them our primary line constants. Now, no finite number of these short segments, just cascading RL, LL, CL, GL, one after another, or, pairwise after another, is going to fully capture the effects exhibited by long lines. It's an effect we don't need to talk about in review. So the short line, we can just focus on the resistance and inductance. So, for length of line less than a 60th of a wavelength. For the medium length transmission line, we focus on just end to end, half of the admittance, half of the impedance, or the full impedance and half of the admittance again. So this is between, a 60th of the wavelength and 20th of the wavelength long. It won't get you the voltage and current changes throughout the length of the line, but it will get you, the sort of end-to-end behavior, how this connects to other circuits. Now, the long TX line equation is something we're going to get to today. And we took a detour by saying, hey, this is the wave equation. It's a very famous second order partial differential equation, where the speed of the wave shows up in it. And then sure enough, when we got the derivation, so we figured out how voltage changes with respect to, distance along the line, using, our differential equation formulations and, KVL in this case, and then how current changes along the length of the line using KCL and the differential equation formulation of it. We got these general wave equations right here, where this says how voltage changes with respect to distance equals this relatively complicated relationship of how the voltage changes with respect to time, and current behaves the exact same way. Notice we get something that looks like 1 over the natural frequency squared. We get something that looks like the sum of time constants, and we get something that looks like, well, just 1 over meter squared, because R and G have canceling units, but remember they're per meter. So we define the propagation parameter gamma, which is going to show up, for the rest of this lecture set, and characteristic impedance Z naught, which is defined as such. And when we write, the PDE with gamma squared, it suddenly looks a little bit nicer. What questions do we have? Right. I mean, some people are retaking this class just to get a better grade. So they did enough to get by early on, but some people are retaking this class as a senior. So I want to know who those people are. Okay. No questions about TX lines. Let's talk about the lossless transmission line. So when the transmission line is lossless, so that means we don't have any dissipative elements like R sub L and G sub L, then this equation right here cancels, because this partial with respect to T term has a coefficients of RL and GL, and this one has both for the function itself. So the wave equation reduces down to the undamped wave equation, no distortion involved, propagation does not depend on frequency. The propagation speed is 1 over square root of L sub L C sub L, which if you work this out, 1 over L C normally has units of radians per second, but we also have the per meter in the denominator, square rooted, that becomes meters per second, units of speed. So when you work these out, you will find that the values have to be chosen such that 1 over square root LLCL is less than, but close to, the speed of light. So you're going to get something that's less than 299,792,458 meters per second, but it'll be fairly close to it. The characteristic impedance simplifies to just Z naught is equal to square root of LL over CL, where Z naught is going to be less than or equal to mu naught times C, where that's going to be 376.73 ohms. Oh, so we get a real number for our characteristic impedance, it's basically just a resistive component. So what happens when you actually solve this partial differential equation? Well, you can kind of guess and check, even if you're not familiar with wave equations. So you'll get one steady state solution. We're going to forget about transients for the rest of this lecture set, because they're just a little bit too hard to deal with. And most of the time we don't care about them too much, because they propagate away from you at the speed of light, or close to it. So the steady state solutions is a forward traveling sinusoidal wave. So we'll say that the forward component of the forward wave voltage, as a function of position and time, is equal to a forward amplitude times sine of omega t minus k times z. So as you can see, it's a function. The sinusoid is sinusoidal in both time and position. So if you were to freeze at one position along the transmission line and look at everything that goes past you in time, you would notice, sinusoidal oscillations. Now, if you were to freeze the picture in time and analyze what happens across the transmission line, you would see sinusoidal patterns. So that's kind of interesting. So we're going to define angular wave number k. We're going to throw a bunch of constants in this lecture set. That's just the nature of the beast. It's just 2 pi over lambda, where v is equal to lambda f, or lambda omega over 2 pi, or omega over k. It's going to act as a so-called spatial frequency with waves. So this is like the spatial component of radial frequency. Or a spatial analog to radial frequency. The second solution we get to our traditional wave equation is the backwards traveling sinusoidal wave, where VB is a function of position and time, is amplitude AB times the exact same sinusoid, except with a plus sign in here. So it's sine of omega t plus kz. So remember, the negative sign travels forward, the positive sign travels backwards. Just how it works when you do all the function transformations. It can be shown, not in this class, but in another class, like electromagnetics, that k is going to be equal to omega times square root of L times CL. And it'll satisfy the wave equation. So we actually have an expression for k now in terms of everything else. So note, also, where does the characteristic impedance come in? It comes in when we start defining the other wave, the current wave. So I is just V divided by Z. Looks like a very simplified version of Ohm's law. So plus VF of Z of t over Z naught. And the backwards traveling current wave is negative VB of Z of t over Z naught. So forward one has a plus sign, and then you need a negative 1 over Z naught for the backwards current wave. So let's prove the characteristic impedance here. So we'll say VF is equal to AF times sine of omega t minus K, which is omega times square root LLCL times Z. So recall that for the lossless wave, a partial V with respect to Z is negative LL, partial of I with respect to T. So we can move things around. The partial derivative of I with respect to T is negative 1 over LL times the partial of this with respect to Z. When we do that, take a derivative, we'll get an AF. Derivative of sine is cosine of the argument. And then we need the derivative of the inside with respect to Z. So we need to bring out a negative omega square root LLCL. But, that cancels with the negative in front of the negative 1 over LL. So we get this coefficient right here. Let's simplify this a little bit. So we'll get AF omega times square root of CL over LL times the cosine. Now we need to pull back into the reaches of our brain, look for how to integrate both sides with respect to time. So we'll integrate both sides with respect to time. We'll get IF as a function of Z and T. So we'll integrate cosine and get a sine. But with respect to time, we need to pull out a 1 over omega. And, we're not dealing with any initial conditions anymore because initial conditions and transients will make things really tough. So we'll just say plus 0 as our constant. And sure enough, take this omega, cancel with that omega. This looks like AF times our original sinusoid, which is just VF, as we said up here. And then this square rooty bit right here is 1 over Z naught. So we prove that IF of T, or IF of Z and T, is 1 over Z naught times VF of Z and T. And if you are so inclined, you could do the same for the backwards traveling wave as well. But, you know, we'll skip the backwards traveling wave. So last thing, we need to talk about the implications of the lossless characteristic impedance. So the fact that the voltage to current wave amplitude ratio, remember it's the ratio of the amplitudes of the waves at the input or output of the lossless transmission line is a constant, should be striking to us. Like that should catch our attention. Regardless of the position along the transmission line or the time that the measurement is taken, the ratio of the voltage to current amplitude remains the same for the steady state solution. So the TX line behaves as though it were a resistor with some sort of, you know, AC resistance of Z naught equals square root of L over CL. So for free space separating the conductors, we get that 376.73 ohms, which is about 120 pi ohms. You know, that's not a trick akin to the square root of 10 is equal to pi. That's, you know, comes from the fact that mu naught is approximately 4 pi times 10 to the negative 7th henries per meter. And if water separates the conductors, so say you just had bare conductors separated by water, you'd be down to 42 ohms. But, you know, depending on the material separating your conductors, you get different values of Z naught. Questions? No questions. So now we're going to, you know, reintroduce everything and talk about the lossy transmission line. So when the transmission line is lossy, that means we have a non-zero R sub L and G sub L. We need the full form of the telegrapher's equations we derived earlier. So in addition to the 4 primary line constants, we're going to talk about the 5 secondary line constants, and we're going to convert everything into the phasor domain. So one of them is the propagation speed, V. That's in meters per second. The characteristic impedance, Z naught, is square root of RL plus J omega LL over GL plus J omega CL. So square root of a quotient of complex numbers is itself going to be a complex number. You know, ZO is an impedance, so it's measured in ohms. We'll talk about a propagation parameter, lowercase gamma, square root of quantity RL plus J omega LL, close quantity times quantity GL plus J omega CL, close quantity. A complex number in 1 over meters. Because remember, each of these coefficients has units of, you know, ohms per meter, henries per meter, siemens per meter, and farads per meter. Attenuation parameter, alpha, is just the real part of gamma. So it's measured in nepers per meter because it's an attenuation. And the phase parameter is beta, which is the imaginary part of gamma. It's a real number in radians per meter. You can see we're pretty desperate for coefficient or for variables, so we just took the start of the Greek alphabet and went from there. Also, you might think something like gamma simplifies a little bit. It does not. There's no simpler way to write it than what I have on the screen in general. So if you were to solve the full form of the telegrapher's equations, you know, and the wave equations associated with them, you have to take, you know, a pretty intense course on partial differential equations. Not too bad, but like, you know, maybe the early part of that course, but like you would need a full course on partial differential equations. We're also going to note that the propagation parameter is just omega divided by beta. So beta is going to fill the role that angular wave number k filled for the lossless transmission line. However, we expect complex exponentials instead of imaginary exponentials, because now that we have loss, this is more like the RLC circuit where we have, you know, real and imaginary components in our exponent, compared to the LC circuit where we had just, you know, imaginary components in our exponent when we're looking at the time domain solution. So we're going to have a 4 traveling wave components with e to the minus gamma z, and then backward traveling wave components with e to the plus gamma z. And remember, gamma is a complex number, so this works out a little bit more complicatedly. So v as a function of z and j omega is af e to the negative gamma z plus ab e to the negative gamma z. A is the forward amplitude, b is the backwards amplitude. And then I as z of j omega is af over z naught times e to the minus gamma z minus ab over z naught e to the plus gamma z. So we get forward and backwards traveling complex exponential. So you'd expect something that looks like damp sinusoids in time, but we're in the phasor domain, so just complex valued numbers in here. So one thing we have to do is figure out alpha and beta. So let's figure out alpha and beta by looking at the derivative of various things. So if we look at the second derivative with respect to position of v of zt, well, that's just going to be, gamma squared times v. So we'll get plus alpha plus j beta quantity squared v z of t. We can expand this. So we'll get an alpha squared. J beta times j beta is minus beta squared. And then we'll get 2j alpha beta times v z of t. We'll also need the time derivative of v z of t. So going back here and looking at what we're going to get here, we're going to get minus omega squared vz of t. And then the first derivative with respect to t of vz of t is going to be j omega vz of t. And this just comes from the phasor definitions. Remember, a time derivative in the phasor domain is just multiplying by j omega. A second derivative is multiplying by negative omega squared. The space derivatives are the ones that are a little bit more challenging to get. So in our full wave equation, we start making our substitutions for every time we see a derivative. So here we're going to see vz of t, and then here's gamma squared. We're going to factor out vz of t from the back, and we're going to get a negative omega squared where we see the second derivative, a j omega where we see the first derivative, and just 1 where we see the function itself. We can simplify, we can separate this into real and imaginary components. Alpha squared minus beta squared is going to be equal to RL GL minus omega squared LL CL. And then, we have J2 alpha beta is equal to J omega GL LL plus RL CL. So looking at just the imaginary terms, we get that alpha is going to be equal to omega times the sum of the time constant looking things divided by 2 beta. But the problem is, in order to get alpha, now we need to know beta. So what is beta? Well, we can rearrange here. So now that we have what alpha is, we plug it into the real part expression. So omega squared, time constant sum squared 4 beta squared minus beta squared equals the real part. And then expand, multiply through by 4 beta squared. We'll get something that looks like this. And we're going to define A to be equal to this bit right here. Should be negative because we normally expect LLCL to be much bigger than the relatively tiny losses LL and GL. RL and GL, I should say. And then B is just going to be equal to, this, what we originally had on this slide, this numerator of alpha. You work this out and you rearrange this, you get 4 beta to the 4th plus 4a times beta squared minus b squared. is equal to 0. This is a quadratic equation in beta squared. You solve for beta squared, and then you take a square root. And this is the simplest expression that I can give you for what beta is for the lossy transmission line in general. Where, not only is there a square root inside of a square root, but we're dealing with constants, which are, I guess constants. They're not really constants. They're functions of frequency, omega. So alpha or A and B are themselves functions of omega and the primary line constants, and that's how you get beta. And then once you have beta, you can go back and get an answer for alpha. Thanks. Questions? No questions. Okay. So this is the general lossy transmission line from slide 38 until slide 42. Let's look at a special case. So let's look at the heavy side distortionless condition. So this distortionless condition is the time constant looking parts are equal. So GL equals RLCL. And remember, there is no a priori reason to think that this condition would be met. It's just so happens if this condition is met, we get a lot of simplifications. So this is a, just so happens type of condition. It's not something that you can do normally. So what you get when this condition is met is the wave propagation speed, v, no longer depends on frequency. In other words, there's no dispersion where you get a separation and distortion of different frequency components depending on how long they've been propagating down the line. They arrive at different times. So you get V is just 1 over square root LLCL, just like in the lossless case. Same thing with Z naught, square root of LL over CL, like in the lossless case. Gamma is equal to root RLGL plus J omega LLCL. So you can separate out alpha and beta from there. Notice that, we still have loss and attenuation, so there's damping going on, but the phase parameter is such that, when we say V is equal to omega divided by beta, the omegas cancel out and we're left with something that doesn't depend, a propagation speed that doesn't depend on frequency. So that means no dispersion in the language of optics. So in practice, the only way you can possibly meet this condition, you don't want to make RL and GL bigger. They are their losses. You don't want to increase your losses. That's a bad way to meet this condition. But you normally find that, the left side of this equation, GL is very, very small compared to RL times CL. So what you do is you make LL bigger by increasing the inductance, LL. And the best way to do that would be to use a magnetic material such as steel if you want to have a practical weight of conductor. So they used to load lines with steel in order to meet this distortionless condition so that the early telegraph cables under the Atlantic Ocean wouldn't, distort dots and dashes. Now, this has fallen out of favor nowadays because we have digital repeaters. So along a long line, every X meters or so, you just put a digital repeater that, reads the signal and then repeats what it sees out on the line to avoid this issue. So instead of having one long transmission line, it's a bunch of medium length transmission lines with repeaters. Another special case we'll look at, from slides 38 to 42 is the low loss special case. So it's when omega L is much greater than RL, and omega CL is much greater than GL. And, for a high enough frequency, this will always be true, right? If you're dealing with gigahertz waves, you should expect this to be true eventually. So V is going to be 1 over square root LLCL. Z naught looks like the lossless case, and that makes sense. you expect this to start looking like the lossless case. And you'll get gamma is equal to this, with alpha equal to 1/2 square root LLCL times quantity RL over LL plus GL over CL. And beta is equal to omega square root LLCL. Notice this is also a dispersionless case, or at least in the limit, it's dispersionless. Our attenuation parameter is independent of frequency, which is very nice, but it's non-zero. So even though it's a low loss line, it's not a no loss line. You'll still get some attenuation, even in the limit of very high frequency signals. And that brings us to the last major thing about, transmission line modeling, what we've been working for like, 26 slides or whatever. The long transmission line equivalent pi model. So if you're only concerned about the input and output behavior of a transmission line, and you don't care about the solution at intermediate values of z, so you don't care about what happens halfway down the line or a quarter of the way down the line or any in-between value of the line, and you also don't care about the physical speed of light time delay of the line, which might be something that's harder to ignore, you can use what's called the long transmission line equivalent pi model. So for long transmission lines greater than a 20th of a wavelength, we need correction factors for z, which remember was in the nominal pi model was RL plus SLL, the length of the line, and the has a shunt admittance. Y over 2 is 1/2 quantity GL plus SCL close quantity times the length of the line. And you get that the equivalent pi model has something that looks like this. So the series impedance is Z times hyperbolic sine of gamma L over gamma L. And the shunt admittance has are Y over 2 times hyperbolic tangent of gamma L over 2 over gamma L over 2. And remember, these, hyperbolic functions with complex argument. So that means you're going to get complex answers when you put complex numbers in to the hyperbolic functions. So it modifies both the resistive and the reactive parts of the impedance and the conductive and susceptive parts of the admittance. And deriving this is a pain. You look at the transmission matrix, you consider both forward and backwards traveling waves, and you make a lot of simplifications, and you notice that you get something that looks like hyperbolic functions. All right. Surely someone has a question about this. Yeah, Riyadh, it's Heaviside, as in Oliver Heaviside. I mean, it's on the equation sheet. You're very unlikely to get something that looks like this. Or if you do, it's going to be a plug and chug question because it has to be a plug and chug question. No, Luke. You're the chosen one. All right. 13 slides. Let's see how we can do. Reflection and transmission coefficients. We understood now how the transmission line, well, hopefully we understand how it behaves in isolation, but now we want to put it into circuits. So we have to consider when the TX line connects to a node impedance at the load side, Z sub L, which could be the lumped impedances of resistors, inductors, and capacitors, or it could be the characteristic impedance of another transmission line. At the load side, you must have the following be true. The ratio of voltage to current must be equal to the load impedance. So VF plus VB in amplitude is divided by IF minus IB in amplitude must hold. The forward and backwards traveling voltages, forward and backwards traveling currents, must combine in such a way that it produces the load impedance. We'll define the voltage reflection coefficient, capital gamma, and the voltage transmission coefficient, capital T, both complex numbers, to determine the relative amplitudes and phases of respective wave components. So we'll say that gamma is defined to be the backwards traveling bit over the forward traveling voltage bit, or just negative the backwards traveling current over the forward traveling current. So it's, how much of the voltage gets reflected backwards at you for every bit that you send forward. And that's complex number, so it can include the phase as well. And the transmission is how much, of the voltage goes into the load relative to the amount you send at it, the forward traveling component. And, there can be a phase shift associated with the transmission component as well. I'm not going to work through the derivation now. Suffice it to say that you plug in, everything involving Z naught, and you work out everything, you factor it all out. You get that gamma is equal to the load impedance minus the characteristic impedance over the sum of the characteristic impedance and the load impedance. You'll also get that, the transmission coefficient is 1 real number plus complex number gamma. And sure enough, you will get that the transmission coefficient is twice the load impedance over the sum of the characteristic impedance and the load impedance. So let's see what happens for special loads. What happens to gamma and T? So for an ideal open circuit, which it's fairly simple to make in practice, so ZL is equal to infinity, you'll get that gamma is equal to 1. Everything that you send forward comes, bouncing back at you, and T is equal to 2. So, you basically have twice of what you send forward goes into the load. Kind of makes sense. There's no load for it to go into. For an ideal short circuit, ZL is equal to 0, and it's very hard to make a practical, short circuit across all frequencies. The parasitic inductance of a short circuit really gets you in reality. So most of the time, what is a short circuit at low frequencies is like an inductor at high frequencies. Then gamma is equal to -1, and T is equal to 0. No transmission at all. There's a short circuit. You can't transmit any voltage or current into it. There's no voltage that goes into it. If you have a match termination, ZL is equal to the characteristic impedance. This is kind of desirable. Then you get gamma is equal to 0, no reflection, and you get perfect transmission. So what you send forward in voltage never comes bouncing back at you. It'll just propagate through into the next transmission line segment. So what happens if you have unmatched terminations on both ends of a transmission line? So you have something that's a source with its, source impedance, and you have a load with a load impedance, and none of them are equal to Z naught. Then what's going to happen is there's wave energy that continually bounces back and forth across the transmission line with an attenuation e to the alpha L for each transit, where alpha, remember, is, the real number attenuation. And, it's going to be negative. So you're going to, get a reduction of energy for every time you bounce forward and back within the transmission line. The energy just kind of stays inside, but gets smaller every time as it transits. So you can create what's called a Bewley lattice diagram. We don't have time to get into that, but that'll track the amplitude of the wave components over time and length. And then, it's a graphical technique that keeps track of your left and right reflection coefficients and attenuation for pulses. If you have multiple transmission lines, basically it kind of behaves like you would expect. If at the end of a transmission line, there's two that join off in parallel, it behaves like parallel impedances. We're also going to define the voltage standing wave ratio because we need more variables to make our lives interesting. So we'll say S VSWR or VSWR is 1 plus absolute value of gamma over 1 minus absolute value of gamma. So whenever forward and backward traveling waves coexist, they create the standing wave, and this will tell you the ratio of the maximum envelope of the standing wave to the minimum envelope of the standing wave. So it's always going to be a number greater than 1 because absolute value of gamma must be less than 1 in all cases. For a single-ended excited pattern. So we have V-SWR, voltage standing wave ratio. I'm not going to bother deriving the input impedance because we're running short on time. But you work it out, based off of the forward and backwards waves, traveling across the length negative L, and you get Zn is equal to the characteristic impedance times load impedance plus the characteristic impedance times hyperbolic tangent of complex gamma L over Z0 plus ZL times hyperbolic tangent of complex gamma L. There's many special cases involved, and this is handy whenever you have stepped lines. So you cascade multiple transmission lines with different characteristic impedances one after another. It basically says, looking into the source side of a transmission line where there's many transmission lines after it, what impedance would you actually measure? Output impedance, well, you just plug in negative L and swap things around where you talk about the source impedance. Instead of that, you get output impedance. So what about in the lossless case? Well, lossless case, gamma is just a purely complex number or a purely imaginary number. So you're going to get Zn is just plus J Z0 times regular trigonometric tangent of KL, where K is the wave number again. So under special cases, ZL is equal to Z0, which means we have a match load. Zn is equal to Z0. This bit right here cancels out. So we're left Zn equals Z0. So we perceive a constant impedance regardless of the length of the line and frequency. So match load is great. It basically behaves like it's just a regular and old impedance. A short circuit, we get a purely imaginary impedance that is periodic in frequency and increasing length. And an open circuit, we get a different purely imaginary impedance, periodic in frequency and increasing length. So if you short or open it, you basically get a purely imaginary impedance when you look into your transmission line from one end. So last two special cases. So this is the special load. What happens if we choose special lengths? So if KL is an integer multiple of pi, that means the length of the line is a half integer of the wavelength. By simplifying this, when we plug in, half integer values of wavelength into the tangent function, we get that Zn is equal to ZL. So the transmission line basically becomes transparent, and we just perceive whatever is connected on the other end. And in the special case that n is equal to 0, this is a very short line approximation because, with the, we're 0 wavelengths long, and none of the parasitics play a role in the circuit. It behaves like a short circuit. So transmission line behaves like a short circuit. You just see the lumped impedance at the other side. Pretty cool. But even cooler is the quarter wavelength transmission line. So say, that where the line is a length L, that's a quarter wavelength of the wavelength. So L is equal to lambda over 4. L is equal to 3 lambda over 4. L is equal to 5 lambda over 4. You look at the input impedance equation right here in the lossless line, and you get Zn is equal to Z0 squared over ZL. So the transformer presents a dual of the impedance. We call this the quarter wave impedance transformer. Another way of stating this is that the characteristic impedance is the geometric mean of the perceived input impedance and the load impedance. Another geometric mean relationship for this class. So under match conditions, Zn is equal to Z0 as before. But what's really interesting is that if you put an open circuit in here, so put ZL equal to infinity, you get Z in is equal to 0. So you can make a short circuit by using a quarter wavelength line that's terminated with an open circuit, unterminated basically. That's pretty. So wow, that allows us to make an actual practical short circuit. For resistive load, we get ZL is equal to R, then Zn is equal to Z naught squared over R. It's resistive, but the bigger we make the resistor at the other end, the smaller the input impedance gets. And then lastly, if we put a capacitor, ZL is equal to 1 over J omega C, then we get that the input impedance is equal to J omega Z squared times C. So the effective inductance is equal to Z naught squared times C. So we've turned a capacitor into an inductor just by using a quarter wavelength long piece of transmission line. And that is all I have prepared on transmission line theory. If you want more, I highly recommend taking 30412, a follow-up to electromagnetics. So this will deal with transmission lines, waveguides, resonators, and the like, antennas. Or ECE 31032, power systems engineering. So the good old-fashioned, power grid, electrical grid operators had to deal with all this stuff. So they dealt with this not only for single-phase power, but also three-phase power as well. So more transmission lines there. And that is all the slides I have made in the normally numbered lecture sets. Claps, everyone. We did it. Barely. So this way we can have those questions on the on homework 7. I don't think I'll make them worth nearly as much as the other questions, but like hopefully those are some give me points if you just look up the proper equations from the equation sheets. Do we have any questions about reflections and transmission and input impedance? I did not do this topic justice. I crammed into, maybe, 2 days, what, is normally 2 weeks worth of content in a normal lecture, in a normal class. But I try to give you a fairly comprehensive view of transmission lines. So please don't fault me for that. Okay. Don't forget about quiz 5. Do your homework 7. Please, please, please take the survey for this class. I know there isn't a lot of time, but try to make time for that. And if you have questions you want to see me work out, please post them on Piazza. Because we will start final exam review on Monday. And I don't want to just sit in front of a quiet classroom. Bye, everyone. See you Monday. You're welcome, everyone. Goodbye.